Hello students, I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. In this video, we will discuss on the measure of relative stability using the phase margin and the gain margin. This video will contain the relative stability, the phase margin, gain margin and the stability condition using the phase margin and gain margin and example. So let's start with what is the relative stability. Now the relative stability actually defines the stability of a system with respect to certain parameter or conditions. Now in Root-Lucas technique we already seen that as the gain is increased, the closed loop system has a tendency to become relatively less stable. And in transient response for the underdamped system, the overshoot increases with the increase in gain, system goes to instability. So this figure is the polar plot of the open loop transfer function GSHS equal to K by S into 1 plus ST1 into 1 plus ST2. Now, there is a tendency for the polar plot to encircle the critical point minus 1 plus J0 as the gain value K is increased. Now, from the graph, we can see that when the K is increasing, this one K1 is K3 is maximum, where K1 is less, and when K1 is increasing, the graph is shown for different values for K1, K2 and K3. Now the closeness of the open loop transfer function G of j omega Hj omega to the critical point, that is the point minus 1 plus J0 point, can be used as the measure of the margin of the stability. And it does not apply to a conditionally stable system. Now, if we consider the polar plot, then we know for the gain K equal to K1, the intersection of Gj omega Hj omega with the negative real axis occurs closer to the origin than that of the polar plot of Gj omega Hj omega having the gain K2 where K2 is greater than K1. Again, when K3 is greater than K2, and then we can see that K3 is intersecting the real axis, negative real axis, a bit longer than this K1 value. Now, the polar plot of open loop transfer function GH with the gain K2 just pass the minus 1 plus J0 point. So, the closed loop system at this stage is just at the verge of instability. That means the marginally stable or the critically stable. Now, the system with gain K1 is actually stable as seen from the corresponding plot. That means the proper design, we can increase the gain beyond K1 before the closed loop system goes to instability. In other words, we can say that we have the margin of gain to play with before the system goes to instability. In this case, the gain margin is positive, gain is still increased from K2 to K3, then the corresponding polar plot encircles -1 plus J0 point, that is the critical point, and the gain margin becomes negative. Or we can say that the closed loop system becomes unstable. Now the open loop transfer function GSHS is a complex quantity and it has both the phase and the magnitude, that is the gain, and the closed loop system stability depends on both the gain and the phase. Now the relative stability of the system under consideration has to be discussed in terms of the gain and the phase, that is the gain margin and the phase margin. So from this polar plot we can say for the value of K1 the system is stable, for the value of K2 the system is marginally stable or the critically stable, and for the value of K3 the system becomes unstable. So we can define the relative stability in terms of the gain margin and the phase margin. Now some important queries may arise while we are discussing the stability of feedback control system, that is, if the system is stable, then how much stability is? That means what is the degree of stability is? That means how much gain we can increase before the system goes to the instability. And another question can become that if the system is unstable, then by what margin of gain the system is unstable? That is, to make the unstable system again into the stable system, then what amount of gain should be reduced? So, we know that for the negative feedback system, if the output becomes unbounded, then the closed loop system becomes unstable. And from the characteristic equation is given as 1 plus GSHS equal to 0, or we can write GSHS equal to -1, and it gives us the magnitude condition, which is the mod of GSHS equal to 1, and the phase condition becomes angle of GSHS equal to -180 degree. So the system becomes unstable, that means it produces unbounded output of these two equations and satisfied, that means the closed loop system stability, the point -1 plus J0, or if we convert it into dB, that means the 0 dB line and -180 degree line, which are very important factors, and we will consider those. So first, for the magnitude condition, we are considering the -1 plus J0 point, the critical point, or the 0 dB line for the Bode plot. If we use the Bode plot, then we will consider it into dB, and if we use the polar uniqueness, then we will consider the -1 plus J0 point, and for the phase plot, the angular reference will be -180 degree line. So next we will discuss on the phase margin. Now if the magnitude of GH is equal to 1, that means unity, if we convert it into dB, then 20 log 1, that becomes 0, because log 1 is 0, and then the closed loop system is just critically stable. So for mod of GH equal to 1, the system becomes the critically stable. That means the 0 dB line is the critical point for determining the system stability gain wise. Now, when we consider the equation mod of GSHS is equal to 1 and it is satisfied, then to make the closed loop system just critically stable phase wise, the measure of phase angle from -180 degree is the phase margin. That is, the margin of phase we can play with phase wise to make the closed loop system just critically stable. And if the angle GH is less than -180 degree, then we can say the phase margin is positive, otherwise it is negative. And for a positive phase margin, the closed loop system is stable, and for a negative phase margin, the closed loop system becomes unstable. And keeping the gain at the critical point, mod of GH is equal to 1 or 0 dB. Now, the beauty of this frequency domain technique is that from the open loop phase characteristics, that is the GH plot, we can measure the relative stability of the closed loop system by finding the margin of the phase that the system possesses before going to the critically stable point. Now, the frequency at which the mod of GH is equal to 1, that is known as the gain crossover frequency or represented by omega g. And the measure of this phase becomes the open loop transfer function at gain crossover frequency from the minus 180 degree line. This one is the minus 180 degree line. So, it gives us the phase margin. That means phase margin is the difference between this 180 degree line and the angle made by the GH. Now, the analytical procedure for computing the phase margin involves the finding the phase of GH omega and H omega at the GCF or the gain crossover frequency and then subtracting 180 degree from this phase. Now, the analytical method involves very tedious computations. So, we will use a graphical method for describing. So, this is the definition of phase margin from the polar plot. Now, the phase margin is actually a measure of the angle between the gain crossover frequency and to the critical point, and phase margin is defined as the angle through which the polar plot of GSHS must be rotated in order that the gain crossover point on the polar plot passes to the critical point. Now, here in this figure, we can show the phase margin is positive. That means the phase wise the closed loop system is stable. Now, if we note that the relative stability information can be obtained from the polar plot of the open loop transfer function. And in open loop polar plot, a line may be drawn from the origin, this dotted line, which will intersect the unit circle which crosses the GSHS locus, and the angle is the phase margin. This angle, that means it is denoted as gamma or the phase margin. It will be positive for gamma greater than 0 and negative for gamma less than 0. So, this one is the locus of GSHS, and then we are considering a unit circle which cut the locus at this point, and as it is unit circle, so we can say this one is the one, that means here this is the gain crossover frequency, and this means mod of GH is equal to 1 over this point. And from this point we can calculate the angle of this angle, and when we can calculate this angle, that is the angle of G of J omega and H of J omega, then we can easily find out the difference from the minus 180 degree line, and that gives us the phase margin. So, the measure of phase of the open loop transfer function at GCF from minus 180 degree line is known as the phase margin, and here phase margin is the angle phi. It is the angle of J omega H J omega minus of minus 180 degree line, which gives actually phi plus 180 degree. So, it is the formula of the phase margin. So, next we will discuss on the gain margin. So, from the relation angle of GH equal to minus of 180 degree, when the open loop transfer function GH crosses the negative real axis, that is the minus 180 degree line or the 180 degree line, then the closed loop system is phase wise critically stable. Now, the frequency at which the open loop transfer function GH crosses the 180 degree line is called the phase crossover crossover frequency. This one is the locus of the GH or the G omega, G of J omega, H of J omega. Now it crosses this 180-degree line at this point. So here the frequency is known as the phase crossover frequency and it is denoted by omega p. Now the measure of the magnitude of mod GH at the phase crossover frequency from the critical point -1 plus J0 gives the gain margin, and that we can play with for design purpose before the system becomes just unstable or the critically stable gain wise. So here this is the phase crossover frequency and we can see that this point is the critical point -1 plus J0 point. So the difference from this -1 J0 to this point, this magnitude is known as the gain margin. Now the physical significance of the gain margin is actually the amount of the gain in the decibel unit that can be allowed to increase the loop before the system reaches instability. So if we consider this figure, so from this figure, this is actually the definition of gain margin from the polar plot. So if we consider this figure, then the phase crossover frequency is omega p and the magnitude of GH at this point is mod of GJ omega, HJ omega at P. That means at phase crossover frequency. Now this we can calculate the gain margin like this 20 log of, actually this is the difference from -1 J0 point. That's why it becomes 1 minus mod of this one, and we know log of 1 minus this thing, that means actually log of 1 by this mod of G of J omega P, H J omega P. If we denote this by capital A, then the formula of the gain margin becomes 20 log 1 by A base 10. Now, if the gain margin is become positive, then the closed loop system is stable. And for the first order or second order system, the gain margin is always finite and hence it is stable for all gain. So these are the stability condition for the gain margin and phase margin. So we have discussed before that if the phase margin and gain margin are both positive, then the system becomes stable. So for the positive gain margin and for the negative positive phase margin and gain margin, the system becomes stable, whereas for the negative phase margin, the system is unstable, but for the negative gain margin, generally the system is unstable. Now, if we consider the first order or the second order system, then the gain margin is always infinite and hence it is stable for all gain, as the polar plot of this first order or the second order system do not cross the negative real axis. And when the critical point is enclosed by the GH plot, the magnitude of Gj omega Hj omega is greater than unity and the gain margin dB becomes negative. So, for the negative gain margin in dB does not always correspond to an unstable system. Now, the minimum phase system, if we consider, then if the both gain margin and the phase margin are positive, then the closed loop system will be stable. And the closed loop system will be unstable if either of the gain margin or the phase margin is negative. And in this is for the polar plot, and in polar plot the measure of gain magnitude of the open loop transfer function at a phase crossover frequency, that is the G of J omega is J omega, and we will put omega is equal to omega p from the -1 plus J0 point is known as the gain margin. Whereas in the Bode plot, a vertical line should be drawn from the phase crossover frequency point of the phase curve to the magnitude curve, and the gain margin is dB obtain from subtracting the mod of Gj omega Hj omega at omega equal to omega p, that is the phase crossover frequency, from 0 dB. And that part we will discuss on the next video. So let us take an example. Here we can see open loop transfer function is given, and we have to find out the phase margin and the gain margin for the given open loop transfer function. So now to find out the phase margin and gain margin, here I am using the Nyquist method. Using the Bode plot method, you also can find out this, and in our next video lecture we will discuss on how to find out the phase margin and gain margin using the Bode plot. So here I have chosen the Nyquist plot. So in this open loop transfer function, there is one pole at origin, and hence I have chosen the Nyquist contour with this fourth section. So for the section 1, here the omega is varying from 0 to plus infinite, and in the imaginary axis all the real parts are 0. That's why I have put in here g of j omega. So g of j omega becomes a sinusoidal function that becomes 500 by j omega into j omega plus 6 into j omega plus 9. And for the magnitude, we will use the formula x plus iy. Magnitude of x plus iy becomes root over x square plus y square. And here magnitude has been calculated as 500 by omega into root over of omega square plus 6 square, that is 36, and omega square plus 9 square, that is 81. And the phase angle that has been calculated as, for this 500 there is no angle contribution, and all the terms are at the denominator. So angle contribution for all these terms will be in minus, and this is omega, or omega means actually it is 0 plus j omega. So the imaginary part is only omega and real part is not there. So tan inverse y by x, which gives us tan inverse infinity, and we will get the value 90 degree. So for single pole at origin, the angle contribution is minus of 90 degree. And for this one, the tan inverse omega by 6, and for this part root over of omega j omega plus 9, for this part the angle is tan inverse omega by 9. So now we are varying the value of omega from 0 to infinite and calculating the magnitude and the phase with respect to these values. So when omega is 0, then the magnitude becomes infinite and the phase angle at omega equal to 0 is minus 90 degree. Whereas when omega is infinite, then the magnitude becomes 0 and the phase angle is minus 270 degree. So this one is the plot for the section 1. So this is the minus 90 degree line. This is the reference line of 0 degree. Then we are going to the clockwise direction. So it is minus 90, this is minus 180, minus 270, and again this is minus 360 or 0 degree. So from minus 90 degree line, the magnitude is infinite, and at minus 270 degree, the magnitude is 0. So this one is the mapping of the section C1. And for the next section, for C2, here we can see this is the actually infinite radius, and this is a semicircular arc where theta is varying from plus 90 to minus 90. So I have put that limit r tends to infinite and r e to the power j theta instead of gs, and theta is varying from plus 90 to minus 90, and due to this the C2 section has been mapped into a circular arc with 0 radius at the origin in GH plane. And for the section 3, if we consider this diagram again, so section 3 has omega has been varying from minus infinity to 0, and this one is the mirror image of C1. So this is just the mirror image of section C1. And for the section C4, if we consider the section, then we can see that for fourth section, this is a very small radius semicircular arc, and hence I have put that r epsilon it tends to 0 and epsilon e to the power j theta, where theta is varying from minus 90 to plus 90, and this is mapped into a circular arc with infinite radius in the GH plane. And as theta is varying from -90 to +90, so it is actually covering the whole right hand side. So this is the complete Nyquist plot. So after getting this Nyquist plot, we have to find out this point of intersection with negative real axis. So this will find out by using the rationalization of the mod of Gj omega. So this is the G of J omega, and by rationalizing we can divide it into two parts. One is the real part and another is the imaginary part. Now in the real axis, all the imaginary values are is equal to 0. So we can calculate this imaginary part with equal to 0. Then we can find out the value of omega, that becomes the root over of 54. So at this point, omega is root over of 54. And if we put this value of omega instead of mod of Gj omega, then we can find out the value of magnitude at this point, which is actually 0.617. As it is in magnitude, that's why it is in plus sign, but actually it is located in the left hand side, and this is minus of 0.61. So this 0.61 is the point of intersection with the real axis. So now we have to find out the phase margin and the gain margin. So here this is the real axis and this is the imaginary axis, and I have considered a unit radius circle. And this unit radius circle will cut the locus at this point, and as it is the unit radius circle, that means this blue line, this is the radius of this circle, and this is 1, and that means at this point mod of GH is equal to 1. So we are going to put this mod of GH is equal to 1. So if this mod of GH is equal to 1, then we can solve this equation, and the solution of the equation becomes omega equal to 5.68. And then we will put the omega value in the phase angle. And from the relation, we have already found out the angle relation, that is this relation -90 minus tan inverse omega by 6 minus tan inverse omega by 9. So when we will put the value of omega over here, then we can find out the angle is -165 degree. So this phi is actually this one, this larger angle. So this is -165 degree. Now we have to find out the phase margin of the system. So how to find out the phase margin? So phase margin is this gap. So for this we can say the difference from this point to this point. So this angle is phi. So the difference which is from phi minus of -180 degree. So it gives phi plus of 180 degree, and this phi plus 180 degree gives us the phase margin is equal to 15 degree. So now this phase margin is 15 degree. Next we have to find out the gain margin of the given system. So to find out the gain margin, first we need to calculate the point of intersection at this point. This point is actually the point of intersection with the real axis, which we have found out in the previous slide, that is 0.617. So I have considered here 0.6. So this point is 0.6. That means this is the magnitude 0.6. So the gain margin is the difference between this, that is from -1 point to this point. So in dB we can convert it into 20 log 1 by A, where A is actually 0.6. That is the magnitude of Gj omega is J omega at this point. That is the phase crossover frequency. When the locus passes the -180 degree line, that is known as the phase crossover frequency. And where the magnitude becomes 1, that is the gain crossover frequency. So from the phase crossover frequency, we can find out the value of gain margin, that is 20 log 1 by A, and in dB it has been converted into dB, so 4.43 dB. So in this way, we can easily find out the phase margin and gain margin. And again, as the phase margin and gain margin both are positive, the system will be stable. And in this way, we can find out the stability of the system. So these are the references